Hi, everybody. Now we are moving on to the derivative of f at x equals b to the power x. So in this case, b is actually a number, whereas e was a specific number. B is representing any number for the base, really any number other than e. So exponential functions, as we know, grow exponentially. So this is just the function f at x equals 2 to the x. Okay, so so in this case, b would be equal to 2. The base is equal to 2. So as b gets larger and larger, our function gets steeper and steeper. The growth happens more quickly. But you can see between 0 and 1, if you have a base between 0 and 1, then you have a decay function. Okay, so that's the rate of decay. Okay, so how does the derivative of that? Well, yesterday we saw the derivative of e to the x was just itself, e to the x. So what about the derivative of an exponential function? Well, you can see here already what it is. Okay, I'm going to turn it on. The red is the derivative and the green is the original. So you can see as we change the original, then the derivative changes as well. And if we have a decay function, then we actually have an upside down or reflected, I should say, derivative. You can see down there. So why is this true? Well, we can see here exactly what's going on. So if we have a function of b to the power x, so in this case right here, 2.5 to the power x, then the derivative is going to be 2.5 to the x times ln 2.5. Now, ln is the natural log. If you look at your calculator, you can see that there is a ln button, ln. If you have this calculator, it's right underneath the log button. So as you can see, as we slide our derivative, it continues to be just b to the x ln b. So if you have a function b to the x, the derivative is b to the x ln b. So why is this true? Well, we're actually going to develop a reason why this is true, and I'm going to have you guys do it. So you can complete the top of this here. So this is the general exponential function, b in the set of all real numbers, and this is its derivative, or what does its derivative look like? So this is what the function b to the x looks like if b is greater than 1, and this is what the function b to the x looks like if your b is between 0 and 1. Okay, so if you go back to the document and fill that in, I actually want you to go ahead and do the investigation from page 235 in your textbook. So it's just going to be this part. So filling in this table and drawing the diagram, and filling in this table and drawing the diagram. And then these conclusions on page 2 we're going to do together in class, because it's a bit confusing, I think, for video. I think you'll get more out of it if we talk about it in person. So I want you to actually go ahead and do this investigation now, and then the rest of the video will be rather short. So, and you will get a lot more out of it if you actually do it, but I will give you the answers just so you can check your work here. So if you want to pause the video or take a screenshot, there's the first answer, and there's the second answer. Okay. So the key here is that you notice that these columns are producing the same thing, this ratio. Okay, so tomorrow we'll go through and talk about the investigation in more detail, go through the conclusions, but for now I am just going to finish up and conclude, give you the conclusion, and tomorrow we'll explain why. Okay, so if you have a function b to the x, then its derivative is b to the x times ln the natural ln of b. Okay, or you can write it ln b, b to the x, either order, it doesn't matter. In fact, actually, I guess this one would be more common because then this becomes a constant, okay, a number. So then you would put that in front of that part. Okay, so for example, if you have 5 to the x, then its derivative is ln 5 bracket 5 to the power x It's that simple. Okay, now if you actually do ln 5 on your calculator, you get a number, 1.609437912. But we don't want to put that because this is just the estimation and we don't want to write that. So we always just write ln 5 or ln whatever as an exact value and simplifies our calculations as well. Okay, so now if the exponent is a function, we are going to use the chain rule. Okay, so if you have b to the power x, then the derivative is going to be, you still have ln b, then you have b to the g at x, so you leave that function the same, times g at x, g prime at x, okay? So you take the ln of the base, then you keep this exponential part the same, and then multiply it by the derivative of the exponent. So f prime at x will be, in this case, ln 5, then 5 to the 3x minus 2, and then just 3, because that is the derivative of the exponent. Okay, so we would actually write this 3 ln 5, 5 to the 3x minus 2. Okay, so just one more example, a word problem here. So on January 1, 1850, the population of Gold Rush Town was 50,000. The size of the population is modeled by P at T is 50,000 times 0.98 to the power T, where T is the number of years since January 1, 1850. Okay, so let's take a look at that. So this means that we have decay, specifically at a rate of 2%, okay? Because each year will be 98% of where it used to be, which is a decay of 2%. So what is the population on January 1? So that is going to 1900. So that is 50 years after. So that is finding P at 50. And that at what rate was it changing? That's P prime at 50. And then increasing or decreasing, well, we know that it should be decreasing because it's a decreasing function, but the sign of the derivative will also give us that information. Okay, so let's find P at 50. Okay, so you just put 50 into the function, and you get 18,208.484. Okay, so obviously this is a population, so we'll do a sentence later, but we're going to round that to approximately 18,208, since you can't have partial people. Okay, now P prime at T, let's just find the derivative function first, is going to be, so we just treat 50,000 as a number. So if you think about it as, product rule, it'd be 50,000 times the derivative of the exponential part of the function plus the derivative of 50,000, which is 0, times that. So we just keep the 50,000 there out front. And then we have ln 0.98 times 0.98 to the t, okay? And no other chain rule because t, the derivative of t is just 1. So there's not really a way to simplify that. So now we're just going to throw 50 into that function, derivative function, and you get negative 367.86, which we're going to round to minus 368 people per year. Okay, so now we need a sentence to answer these questions. So in January 1, or on January 1, 1900, the population was approximately 18,208 and decreasing at a rate of 368 people per year. Okay, so that all answers all 3 questions: the population, the rate it was changing, and whether it was increasing or decreasing. Okay, so now we have our success criteria. Can you find the derivative? Okay, and then after tomorrow in class, you should be able to explain the process that we use to discover this derivative. Okay, so thanks for watching, guys. Hope you learned lots.